so we do have a problem set, and there is, as you may know, that we're having our annual open house for our recruitment of graduate students, and that's happening in room 190. So we'll see how it goes. There is a gap there at 10 to 11 where the students are going on lab tours, so we can maybe see into our Prof session. Otherwise, we'll maybe go down to room 30. Okay, I'll meet you at 190 on Friday. We'll decide. All right. All right. Very good. So last time, what we talked about Fermi's golden rule. And Fermi's golden rule is often written this way. What it says is that the rate of transition from some initial to final state, depending upon whether one is going to a higher energy level, one is absorbing energy, or one is going to a lower energy level, one's emitting energy, is expressed here in terms of the matrix element between the initial and final state of the interaction, appropriate interaction Hamiltonian, and then this energy conserving delta function. Okay? So that's how it's often written. As we discussed, what that really means is this only makes sense in the context of an integral. Delta functions really only make sense in the context of an integral where you're integrating over a distribution of possible, say, energy levels or possible excitation frequencies when you have broadband excitation. So other ways we could write Fermi's golden rule are written here. We could have a situation where, for example, we don't have a definite energy level because we have some energy band for some reason. It might be we're talking about a solid or a whole band of energy associated with the rho vibrational states of a molecule, or we have lifetime broadening of the level. So there's some density of states at the final energy corresponding to absorption or emission. And that density of states then would replace the delta function. Or we might have a situation where we have a lamp or a black body which has an incoherent spectral width, and the density of modes of the field at the frequency corresponding to the transition that one's making would then replace this delta function. So these are three different ways that you'll see Fermi's golden rule expressed. Okay? And the important physical point here is where do we apply Fermi's golden rule versus thinking about Rabi oscillations, coherent evolution according to probability amplitudes evolving according to the time-dependent Schroeder equation. This is more of a probabilistic rate equations rather than coherent evolutions of probability amplitudes, okay? And this kind of description is applicable when what I would call the coherence time of the system, the time in which there is a good phase relationship in the system. And that phase could be phases of the exciting field. It has a well-defined oscillation or before the phase information gets lost for some reason. Or it could be intrinsic phase evolution of the system because of this broadband density of states. If that coherence time is short, or as long as the time that we're looking is long compared to the coherence time, then we can forget about coherent evolution and think about rate transfer. In that regime, Fermi's golden rule applies. Okay? So A couple of examples we studied last lecture was thinking about the interaction of a atom with a broadband field, and there what we found is that the rate of either absorption, which is equivalent to the rate of stimulated emission, is proportional to the spectral energy density of the exciting or de-exciting field at the resonance frequency times some coefficient that is a property of the atom, okay? And that coefficient is known as the Einstein B coefficient, and it depends on the matrix element of the dipole, assuming that that matrix element's not zero, okay? And finally, we discussed the situation where we're in the excited state and there's no field applied, but nonetheless, the system undergoes a transition to a lower energy level, and that is the process of spontaneous emission, which is intrinsically due to the fact that the atom is always interacting with the quantized electromagnetic field. So it's in some sense a property of QED, but we derived it as Einstein did before there was QED, just from thermodynamics, right? That there had to be, if you have an atom bathed in a black body that is at temperature T, then that atom has to come to steady state and have a thermal distribution given by the Boltzmann distribution. If that were the case, we had to have this dissipative effect. And what we found is that the spontaneous emission rate, which is sometimes known as the Einstein A coefficient, is equivalent to stimulated emission by 1 photon. Okay? But as I mentioned, it's a little bit of a misnomer to say that's 1 photon in the vacuum that's doing it, because the energy fluctuations of the vacuum is a half of h bar omega. So where the heck did a full h bar omega come from? Well, there's some subtle points having to do with, there's two kinds of effects. One is fluctuations, vacuum fluctuations, but there's also radiation reaction. Both of those terms contribute to give you the full h bar omega. All right? All right, any questions about any of that? All right, let us continue then. So one of the things that we discussed is that when we talk about the interaction of light and matter, that what we have typically a situation in which the wavelength of the light is big compared to some characteristic size of the dipole. Or I should say the charge distribution. And when that is the case, as we've said, then it is much more convenient to think about the interaction Hamiltonian in terms of a multipole expansion. Okay, so we would have some kind of expansion that looks like this. So the nature of this interaction is that there are moments of the distribution. There's the electric dipole moment, there's the magnetic dipole moment, there's the electric quadrupole moment, there is the magnetic quadrupole moment, et cetera, et cetera, et cetera. And in that situation, then, as we discussed, the dominant interaction under this condition would be the electric dipole. That's typically what we would do, but it might be the case, for example, go back over here, and I kind of said this as an aside, unless the electric dipole moment vanishes. For example, suppose the ground state were an S state, but the excited state were a D state. D states have L equals 2. Okay? And we know from parity selection rules that the dipole matrix element vanishes in that situation. Well, then we'd have to go to the next order, and we'd say, well, maybe there's a magnetic dipole associated with this. Well, then we'll find actually, no, that doesn't work either for a different reason. Then we have to go to the electric quadrupole. In fact, that's a quadrupole. We'll talk about that. That's a quadrupole transition, electric quadrupole transition. So the reason I'm discussing this is to motivate the point that we need, if we really want to understand the interaction of matter and fields, we need to think about the theory of tensors, vectors and tensors, in quantum mechanics. Because it's that theory that tells us something about selection rules, it will tell us something about the strengths of those transitions, the lifetimes of those transitions, and more general aspects of the interactions of matter and fields. Okay? So that's what we're going to do for the next number of lectures. Number to be determined. Okay? So what we're talking about now is the theory of tensors in quantum mechanics. All right, so to go there, we need to first think about, well, let's start with vectors, okay? So let's just think about, what do we mean? What do we mean by a vector or a tensor? Let's just think, firstly, if we think about in classical physics. Okay? So, well, a vector is something which looks like position in some sense. The definition comes from what we mean by the position vector. So if I have a position vector, right, with x that we'll generally write as having components is for convenience either x, y, z. Then these components are, of course, relative to a basis, and we have some kind of position vector, right? The property of this vector is that if I change the basis, and in particular if I change it in such a way that I rotate the vector, so this is an active rotation of the vector, that the new components of the vector, of the rotated vector, are related to the old components by a rotation matrix, right? So I'm going to use the Einstein repeated index summation convention that I'm very familiar with. And so my R, I'll write my matrices in this, I don't know what you call this font, the one with the, whatever, that kind of font.
Blackboard bold.
We'll call it Blackboard Bold. I'm half a Blackboard Bold, so it works. All right, so this is a rotation matrix. And it's defined such that, of course, what a rotation does is it preserves the norm. Right, so that is to say, the norm of the rotated vector is the same as the norm of the original vector, right? And the norm of the, so this is equal to the square, the sum of the squares, repeated index here, that's thus equal to R I J X J R I J prime X J prime, and that has to equal X J X J. Right? Which means that the rotation matrix must satisfy delta J prime. Okay. Which is to say, if you, this is of course equal to Rji transpose Rij prime, is delta J prime, which is to say that the matrix R times R transpose is the identity matrix. Or equivalently, this you can do it the other way around, and it would also be true. Okay? If you sum the right matrices differently. So such a matrix, this matrix is a whose inverse is equal to the transpose is known as an orthogonal matrix. In this case, in 3D, three-dimensional matrices. Okay. Now, the particular kind of transformations that we're making here are ones that are what we consider proper rotations. And what I mean by that is a rotation that preserves the handedness of the Cartesian coordinates. Okay, so for example, a transformation that just permuted the coordinates would preserve the norm, but this is not a proper rotation. What it corresponds to is an inversion of, in this case, y and z, leaving x alone. So this is a inversion. It's not a proper. Or this is a reflection. Okay? Not proper. if you restrict yourself to that case, what you find is that the determinant of this matrix must be 1. Okay? So proper rotations are ones that satisfy the condition that the inverse is the transpose and they have determinant 1. Okay? And that set of what we call special orthogonal matrices in 3D. And that set is special orthogonal matrices in 3 dimensions, SO3. Okay? So that's what the S stands for in SO3, special. So by analogy, thus, we define a vector V as any 3-component object with respect to some coordinate system, such that it transforms according to the same orthogonal transformation. Okay. So if it transforms like this, we call it a vector. All right, more generally, we define tensors of rank K. So a tensor of rank K is some object which, with respect to some coordinate system, in the same way that we have the coordinates of the vector, we can have coordinates of the tensor. Okay? So it has, if it's rank K, it has K indices. 1, 2, 3, 4, up to K. So these are the components of the tensor. And if we're talking about 3 spatial dimensions, how many components are there?
Three to the K.
3 to the K, right? Because each one has 3 indices, and then you have K of them, so each time. Yeah?
So are we only doing like contravariant, or like only one kind of?
Well, so at the moment, these components are respect to a Cartesian coordinate system, so there's really no difference between the basis and the dual basis. Where we're talking about, I mean, so here what we're interested in, and this is going to be part of the thing that we're going to have to keep in mind, there are 2 kinds of vector spaces when we get to quantum mechanics that we deal with. There's 3-dimensional space, then there's Hilbert space. There's going to be some mixing of concepts here. But as far as right now I'm talking about the classical physics, we'll come to the quantum mechanics in a moment. We're talking about 3-dimensional plain old flat space. All right, so these are the components of the tensor with respect to some Cartesian coordinate system, right? So each of these index I can be 1, 2, or 3, representing x, y, or z. So now, the tensor, like the vector, is a geometric object. I can rotate it. So what defines a tensor is how the components look in a rotated, as if I rotate it. That's what defines the tensor. So if it is a tensor with respect of rank K, then under a rotation, the rotated tensor has these components, and it's related to the components before the rotation according to a series of rotations. So I apply the rotation matrix to the first index, I apply a rotation matrix to the second index, etc. Times T, J1, J2, dot, dot, dot. Oops, that's it. All right, so again, this is I'm using the Einstein repeated index summation convention. So I sum over J1, I sum over J2, I sum over J3, all the way up to JK, and I'm left with an object where these are the free indices, I1, I2, up to Ik. So that is by definition. So let's just look at one simple example, okay? So let me define the dyadic position. Okay, so that's my double-headed vector, yeah.
What does it mean when you have that?
So what does that mean? So this really is what I should think about this as, instead, this is an outer product. But I don't put anything.
Like a wedge?
I can't say that, but like a wedge product. I'm not positive about that, Keith, so I'll come back and remind myself in what context that makes sense. But really, you should use this just like the outer product, the tensor product, more like a chronicle product, like we know from two cats. So what this means is the following. This literally means it's an object which has, so the outer product of two vectors is this tensor, which I could think about writing as a matrix if I wanted to. So this, I could think about this as a 2x2 matrix, right? Where this is x squared, y squared, z squared, xy, xz, yx, yz, zx, zy, etc.
So the property of the dyadic, what do you call dyadic? The fact that if I would sum over various vectors xi, x, have a set of vectors, and then I sum over them.
There's no sum written as here. This is really an outer product. So I'm not summing over anything.
Yeah, but suppose I have, so dyadic is like a pure, well, I just know.
I'm not sure what,
So
all I'm saying is by definition, it's an object whose components are this.
Okay.
I don't know what more to say,
Okay.
than that's what it is.
Okay.
So it is the outer product of the two vectors.
Okay.
It's just a way that you often write. So you don't want to have to write a symbol. I could write here if I wanted to that. That would be equivalent.
But what I meant is not every rank 2 tensor is dyadic.
That's correct.
Okay, but
Not every rank 2
That's
tensor is
what I-
dyadic,
okay.
but every dyadic is a rank 2 tensor.
That's what I was.
Yep, absolutely. In the same way that not every, if I have a tensor product, you really should think about it exactly, it is the tensor product.
Yeah.
It's just we typically don't write it.
Yeah.
We just write it like that. Okay? So just for fun, I mean, if I look at this, if I rotate this, that's equivalent to rotating each of these vectors. So the rotated dyadic, right, that's rotated this vector with rotated this vector, tensor product. That's what it means. And that says that these guys are equal to Rij, or I prime, J prime, which is I prime, J prime, R transpose J prime J, which is R T I T R transpose I J. Right? Which is just a similarity transformation with respect to an orthogonal transformation. Okay, so this is kind of a multi-dimensional matrix. You can think about this, and this is just a similarity transformation with respect to all of the dimensions of that matrix. All right, so what we see here is that what we mean by vectors and tensors is intimately related to rotations, the actual physical rotation, how it behaves under a rotation, in this case in 3D, okay, of physical space. So the set of rotations is a group. So let me just quickly, I'm going to say just a few words about groups and group theory. Of course, it's a very sophisticated subject, an important subject in theoretical physics, one I wish I knew better. I spent some time doing that. Nonetheless, we'll give you some flavors that are important for what we're going to study, because it's obviously intimately related to what we're discussing here. Okay? So we have the set of rotations is a group. What do we mean by a group? Let's remind ourselves. So first we need to try. All right.
So in some sense, it's meaningless to talk about, a particular mathematical object as a tensor only if you think of the set of tensors which is generated by the group of rotations.
What I would say is that a tensor is a geometric object, and that geometric object behaves a certain way under the set of rotations. If it behaves that way under the set of rotations, then we say it is a tensor of that rank. Okay, so let's just remind ourselves quickly about groups. So G is a group. Okay, and it has the following properties. We have or a composition rule. That is to say, there exists an operation such that for two elements of the group, we can compose them in some way with some effective composition that's inside the group. That's what makes it firstly. It's more than just a set, it has this composition rule. It's associative. That is to say, I can first compose A with B, and that's the same thing as A composed with what you get when you compose B with C. There exists an identity element, which gives you back the element when you compose it either on the right or the left, and there exists a inverse, which, when composed with the element, gives you the identity. Okay, so those properties define the set G to be a group. In particular, there's when, and I'll speak somewhat loose and not completely rigorous here, but try a little bit. When G forms a smooth surface, more precisely a manifold. So when the elements of the group are a continuous set, and when that continuous set can be described as a smooth surface, more precisely a manifold, then we call it a Lie group. So a Lie group has additional structure beyond these rules. It has this notion of a geometry, okay? Now, Lie groups, because I have this notion of continuity, because it's smooth in some way, I have, and we've talked about this before, we have the possibility of near identity. Elements. So I can have an element of the group which is equal to the identity plus some small amount times something else, I'll call A, okay, for some epsilon. Let's leave it like that. So this is small. Epsilon goes to 0, this would be the identity. Okay? And because I have that, I can get from there to say that every element of the Lie group can be expressed as the exponential of something else. Okay? And the set A is not, they're not elements of the group, they're something else. And these things are known as the Lie algebra. So we have a Lie group, and we have a Lie algebra. But as we discussed, and we discussed this a little bit last semester, we think about A as the generators of the elements of the group. Okay? Now, a couple of other definitions. Because this thing is a manifold, the surface, it has a certain dimension. For example, the sphere is manifold. It's a manifold in 2D, right? Because it's a surface that locally looks flat. I mean, you know, the flatlanders still believe that. So it's a two-dimensional manifold. So a manifold locally looks flat. So locally, it looks like a Cartesian space, right? Like we put a grid here on the sphere. What that means is that, so there's a locally flat, and it has a dimension d. Okay. What that means is that, what do we mean by the Lie algebra? The Lie algebra has some structure. And one structure it has is that it's a vector space. Just like on the surface of a sphere, I can put a local xy grid locally near the surface of the sphere. And there's a vector space associated with different directions going, east or west, for example, or north-east, north-south. So it's a vector space, which means that every element in the Lie group, in the Lie algebra, can be written in terms of a basis vectors for the Lie algebra. So I can write this as so my EIs are basis elements of the Lie algebra. So if I wanted to say, for example, on the sphere, go in that direction, I could say first go, 3 blocks east and then 2 blocks north. And that will get me somewhere locally near the surface. Okay. So that means that we can generally write this, for example, as exponential, like that, for some basis of the Lie algebra. Or I might write it like that. Lie algebra has another structure that makes it a Lie algebra different from just any old vector space, and that is that there also exists a Lie bracket, which has certain properties that aren't so important for our notion. That is a different kind of composition law. If I have two elements of the algebra, A and B, I have something I call the Lie bracket. And for our purposes, that will be the commutator. We'll see that in a moment. Has to satisfy the Jacobi identity. We're not going to get into the depths here. All right, so for example, let's talk about the group of rotations in 3D. Consider SO3. Okay. So SO3 were the set of matrices, 3 by 3 matrices. Just again, these are 3 by 3 matrices. That are orthogonal, meaning their inverses, their transpose, determinant of 1. That's the set. Okay? This is a group. The composite, any two rotations in sequence is in some other rotation. Okay? There is an inverse, right? You can always find that by the transpose. We have the identity. So in this case, it's a group. With composition matrix multiplication. Inverse transpose. Identity the identity matrix. Okay? It's also a Lie group. Now let's think about the Lie algebra of SO3. So to do that, let's think for a moment. Let's talk about near identity. Okay. So let's say I have some R in this group, and I'm going to parameterize it by an axis and an angle. So this is my axis angle parameterization of the thing. Okay? Every rotation matrix is rotation around some axis by some angle. The composition law is actually complicated to write this way. If you were to say, rotate around this axis by this angle, and that axis by that angle, and then I ask, what axis and what angle does that? That's actually a messy expression, but who cares? So let's look at this for the case where I have a very small angle. Approaching a differential. So this is approximately equal to the identity plus this, where it's some element of the Lie group for that axis. Okay? So this is element of the Lie algebra. And by the way, we often talk about the Lie algebra, we write it with a small letter. So the Lie algebra is little SO3. Okay? So now I ask, we want to know what defines these matrices. These are all old blackboard. 3x3 matrices here. Okay, it's the identity matrix. This is some other 3x3 matrix. What defines the set of 3x3 matrices such that this is in the Lie algebra little SO3? Well, what has to be true, what defines this is that it's an orthogonal determinant 1 matrix. Right? So let's look at if this is orthogonal, it must be the case that when I multiply it by its transpose, I should get the identity, right? And that is equal to this times this transpose. Let's just write it out. Right? And so let's come back over here. So it says that if this is a differential, then I only keep the linear terms. Okay? Which has got to be equal to the identity. So what that tells me is that if this matrix is in the Lie algebra of SO3, then it must satisfy that it is an antisymmetric matrix. So the set of antisymmetric matrices define the Lie algebra. Okay? What is the dimension? Is a little bit maybe. What is the dimension, firstly, of the Lie algebra, which also defines the dimension of the manifold? How many parameters I need to define the group? What do you think?
6, no, 5. Was it 4?
So what defines this? How many real parameters do I need to uniquely specify an element of the group?
4.
Where's that coming from?
Well, I mean, x, y, z, and then the angle? Like x, y, z of the and vector and then the angle?
Close. It's a little bit just, n itself is not an arbitrary vector, it's a unit vector. So there's how many parameters does it take to specify a unit vector?
Just 2.
2, because I just need to know the direction. I don't need to know its magnitude. Its magnitude is set at 1. So there are 3 parameters. So this is 3-dimensional manifold. It's related to the actual manifold is S3. Oh, actually, maybe not that might be an issue. Anyway, I don't remember. Sorry, come back to that. All right, so that means that we should be able to express any element in the Lie algebra of SO3 as a linear combination of 3 basis vectors in the algebra SO3, in the way that I wrote it over there. So a basis for SO3 would be the following. Any set of completely anisymmetric matrices that are linear independent form a basis SO3. For example, here's a basis. I'm going to define, so let me explain this notation. And this is by convention, this minus. So I have 3 vectors. I mean, well, not vectors. They're kind of vectors in the algebra. There are 3 3x3 matrices. I have I1, I2, and I3. These are 3 matrices that I claim form a basis of the Lie algebra. And these matrices, their matrix elements, so the matrix element of this are these. Let's write it out. So I1, let's write the first one down. So if it's an anisymmetric matrix, all the diagonal matrix elements are 0, right? It's got to be, otherwise when you flip the sign, it wouldn't be itself. And that's true. So the first element is epsilon 1, 1, 1, right? That's what this means. And that's 0. Then, all the diagonal elements are 0. Then I have epsilon 1, row 1, column 2. What is that?
0.
0. 1, 1, 2, right? So these guys are all 0. Row 1 is 0. Now I have epsilon row 1, column 2. Row 2, column 1, right? This is row column. This is also 0. And now I have this guy. We have epsilon 1, row 2, column 3. So that's 1, and this becomes minus 1, right? And then this guy is plus 1, and that's 0. So that's one of these guys. I'm not going to do that all. I just write it down. I can never get this straight. Oh, I got it right. This guy looks like this. And this guy is the guy with these guys, -1, 0, +1. Okay? And what I claim is any antisymmetric matrix in the Lie group, in the Lie algebra, has the form and that matrix is, it's minus C times this, plus A times that, minus B times that. So any antisymmetric matrix is a linear combination of these three basis matrices. Therefore, the set here is a basis, and moreover, it's a Lie algebra with respect to the bracket. So my Lie bracket is the commutator. And with a little bit of algebra, you can show the following is true. The commutation of any two of these basis matrices is one of the third one is f on ijk, sum of k. This defines the Lie algebra SO3. Okay? Now, note, this looks kind of, we're getting there, we're getting to quantum mechanics and its relationship to all this. There's angular momentum and rotations.
There's no I over H bar.
There's no, not yet. Now, of course, I could define a different way of defining the Lie algebra by factoring out of so right. I could define a set of matrices J, say case 1, as minus I times those guys. I could define those. These guys are Hermitian. Why? If I look at J dagger, that's plus I times I dagger. But the dagger in this case is the transpose, because these guys are real. So this is equal to this. So these are Hermitian matrices. And then every element in the group is equal to e to the minus I j, or some k jk, or k not the vector of matrices. Looks getting closer to something that looks like quantum mechanics. And if you look at these guys, their commutators satisfy, using just that definition, the Lie algebra with respect to these matrices J, which are a perfectly good way of describing the Lie algebra, is exactly the commutation relations quantum mechanics. Right, just plug in this definition here, and you get back that. These are two different ways of talking about the Lie algebra of SO3. Okay, now I want to make one aside here. And that's an important one. So I want to talk about group representations. So when I first mentioned the group, I didn't say anything about matrices. I just said there is some set, and that set had certain properties. There was an abstract composition law, and it just had, it was a particular mapping of two elements to other elements in the group. Okay. So I want to talk about there's something that we call an abstract group G, which is just some set with composition and all the other rules. Okay? And I can have some elements in the group. Now, I can have a mapping of elements into that of the group to any other set I like, as long as there's a way of that it respects RESPECT, the composition laws and the inverses, and it's a representation of the group. Okay? So one way I can have a representation of G via matrices. That is to say, I can map every element of the group to a matrix. I'll call it D of A. This is a matrix. I'm not saying what it's a matrix of any dimension, it's just some matrix. And this is a representation if A composed with B is equal to the matrix multiplication of those two, such that this is the same as the matrix you get when you compose them. Okay? Moreover, I have to have it be the case that I map the identity element of the group to the identity matrix and the inverse element to the inverse matrix. Okay? That is what's known as a matrix representation. Generally, there exists an infinite number of different representations. There's not a unique way of doing this. There's always one way of doing it. It's a very trivial way. There's the trivial representation. For example, I can map every element onto the identity matrix. I could do that. Watch me, I did it. Does this satisfy all these rules? Sure it does. Because every one I compose, it's it. Oh, I'm in it. It's all the identity. It doesn't matter. It satisfies all the rules. It's the trivial representation. We'd never do it, but we could. Okay? One of the things, just a reason for saying this, is that the representation need not be one-to-one. I can map two different elements of the group onto the same matrix, and it can still be a representation of the group. In this case, I mapped all elements onto the same matrix, and it was a representation of the group. Okay. Now, the group SO3 has a defining representation in terms of 3x3 matrices. So we define the group as a group of matrices, or a set of matrices. But, as we will see, I can represent the same group by other matrices that are not 3x3, but yet respect the whole group structure, such that composition is what we want it to be, and inverses are what we want it to be, etc., etc. Okay. Okay. Now, another important concept is the notion of reducible versus irreducible representations. A very important concept. So, given a representation of the matrices, if I write a new representation in terms of some, maybe I should make these bold, blackboard bold. Just emphasize these are matrices. In terms of a, so this is just a change of some other, this is a similarity transformation. These S's aren't necessarily elements of the group, but I just did a change of basis. So this is a similarity transformation. If I do that, then this is also a representation. Right? So if I just change the basis, it's all going to satisfy all the same laws. I can do that. But this is what we would call an equivalent representation. This is equivalent. It's really not a different representation. I just changed the basis. It's the same sort of essential matrix. Okay? Okay. So, if by some similarity transformation my representation can be written in the following way. If I can diagonalize this into different blocks, more than one block, So if that's true, then we say that the matrix or the representation is reducible. This is a reducible representation. Why is this reducible? Well, what you see here is that, and this has to be true for all, if by similar transformation, this is true for all A in the group. So it has that same block diagonal form. If it has that form, then what you see is that each of these subblocks is itself a representation of the group. So I have now, in some sense, 3 different reps. I have this one, right? Because I multiply them together, they're going to satisfy the blocks, they're going to satisfy the composition block. This block, and they don't have to be the same dimension. This could be a 1 by 1 block. This could be a 10 by 10 block. This could be a, 137 by 137 block. Doesn't matter. If they're all these different blocks, these correspond to different representations. Okay. So, by contrast, if we cannot further block diagonalize, then we say that this is a irreducible representation, or an irrep. And it's very important in the structure of groups that the whole groups are defined by their irreps. Once I have the irreps, I kind of have the whole story, as we will see. All right, well, let me finish this lecture by just beginning to talk about now the quantum problem.
By definition, if you are able to diagonalize it like that, then you find the irreps, or it's not?
Finding the irreps is a more complicated problem than just diagonalizing. I mean, you've now written, in this case, what I've written this representation as a direct sum of the irreps. But what the irreps are and how you find them is a more complicated story. All right, I want to just begin to talk about the quantum. Okay, so in quantum mechanics, we have a rotation operator on Hilbert space. This is not the same thing as the rotation matrices that acted on 3 spatial coordinates, although there is an intimate relation, as we will see. That Hilbert space could be a 2-dimensional Hilbert space, it could be a 3-dimensional, it could be an infinite dimensional Hilbert space. Depends what we're talking about. Okay? So let's call those operators D. And we might write them in terms of an axis and an angle. Okay. Now we know what those operators are. Those operators are e to the minus I, the angle axis times some angular momentum. For now and for the rest of these lectures, h bar is 1. J is in units of h bar. So J here are the components of angular momentum and satisfies these commutation relations. Okay. Now, the relationship to rotations in 3 dimensions is seen through the unitary transformation. That is to say, rotation via unitary transformation. So if I look at the unitary transformation on the components of position, so this is x, y, or z. That's a unitary transformation on position operator. What is this? Well, that's the rotated position. And the rotated position has new coordinates. Those coordinates are given by okay? So for example, if I rotate it around the z-axis, by an angle phi, and I apply that to the x operator, where this is e to the minus I phi Lz, the orbital angular momentum operator. That's Pythagoras plus. What is this? Well, it's cosine phi x plus sine phi y. I just rotated around that, and that's okay. So, on the left-hand side of the equation, I have the unitary transformation on the operators, and what that affects is this transformation. There's 2 kinds of things going on here, right? There's this guy, which was, the rotation matrix that in 3 dimensions, and there's this guy, which is the unitary on Hilbert space. Keep that in mind, all right? And generally speaking, we could say the following. We define a vector operator in 3 spatial coordinates as a set of 3 operators. And it is a vector operator if it satisfies the property that under a unitary transformation, this is the rotating vector. That defines a vector operator. I could define a tensor operator. Which has 3 to the k different components. And this, again, it must be the case that if I do the unitary transformation on this, I get this usual transformation on the components. So for example, is a rank 2 tensor operator. And what we want to study are the properties of these tensor operators. Now, just one last comment before we quit. In the three-dimensional space, this was the group SO3. What about these guys? Are they also SO3? No. And we're going to see those are actually in the group SU2. And we're going to talk about the relationship between SU2 and SO3. Yeah?
Does that depend on the dimension of the Hilbert space?
No, those are different irreps of SU2. So it's all SU2, but different irreps for different dimensions. All right. Very good. Have a good afternoon, everybody.